Hi, welcome to Nanotalks. This Nanotalk is a recording of a webinar in which we showed how In Situ TEM advances catalysis research. First, you will hear our product manager Ronald Marks, who will introduce the climate system to you. And then, Dr. Dan Zhu will present various application examples and will show you how In Situ has enabled a complete Operando analysis. Our CTO, Hugo Perez, will be handling the Q&A at the end. I hope you enjoy this Nanotalk.
All right, I will now start the presentation about how In Situ TEM advances catalyst research, which is focused on in situ gas and heating for TEM. So DENSsolutions has a product portfolio of 4 In Situ TEM systems. We started back in 2012 in the town of Delft in the Netherlands with making In Situ TEM heating system, which we called Wildfire, based on MEMS technology in the tip of the holder, which serves both FEI and JL microscopes. A few years later, we extended the range to In Situ biasing and heating, which is called Lightning, and also In Situ gas and heating, which is called Climate. And then more recently, in the last 1.5 years, we upgraded our older liquid system to Stream, which is the In Situ TEM system for liquid with biasing or heating. So four systems in our product portfolio, but today we will focus only about climate, In Situ TEM gas and heating. Climate has 4 main applications. Most important application is heterogeneous catalysis, but we also have a lot of customers and publications who are in the field of nanomaterial growth and synthesis. 2 other applications that we will not be discussing today, but are still linked to climate, are corrosion and green energy materials. But let's first start with the main application, which is heterogeneous catalysis. So for catalysis, you have a bit of an issue in scale and size. Catalysts are used most of all in fab environment, large-scale chemical processes where you have reaction vessels of 10 meters or maybe more, so really huge. But then the catalysts themselves are most of all nanoparticles which operate at the nanoscale. And if you want to understand what they're doing, you also need to look at the nanoscale, which brings you to TEM research, because that's the only way we can really observe events happening at this nanoscale. So the question is, what could be the smallest chemical reactor that can fit inside a TEM? First of all, you transform your chemical reaction from the fab into the lab. So, for instance, you take an Erlenmeyer with content of 100 milliliter or so, but that still is much too large to observe nanoscale events in the TEM. For that, you need to have a nanoreactor, and that's exactly what we made for climate. A nanoreactor made of 2 MEMS chips in the climate holder to transform the catalyst process from fab scale via lab into a macron size reactor where you can observe events happening at the nanoscale. But climate is not only a TEM holder for JL or Thermo Fisher. Of course, it also requires the MEMS chips to make the nanoreactor. So each nanoreactor is made out of 2 chips, a bottom heating chip and a top cover chip. They come in a box of 5 nanoreactors. And climate system also includes a tool so you can align these 2 chips on top of each other, so the beam will nicely penetrate the nanoreactor. Then, of course, for in situ gas and heating, you need a gas supply system. We have this very nice gas supply system, which can hold up to 3 gas cylinders that are mixed by means of mass flow controllers. And then it has a swing arm with pressure controllers that can be maneuvered very close to the TEM holder inside the column. Inside this gas supply system, you also find a small electronics box which will control the heating function of the nanoreactor. Then, of course, the whole system is software controlled via a laptop with Impulse software. We'll come to that a little later. Laptop can also be located remote if you have a control room outside of the actual TEM lab. That will also work very well via this laptop and an Ethernet connection. Finally, there is a gas analyzer as an option to the climate system, where you can analyze the gas flow coming out of the nanoreactor via a mass spectrometer. And first, let us take a closer look at the nanoreactor inside the tip of the in situ TEM holder. So you see the bottom chip with the heating membrane and the metal heater, which is now heated. And here you see the gas flow going from the gas inlet to the gas outlet, flowing over the sample on the heater. And here you see the complete nanoreactor inside the tip of a holder. Actually, this is the Thermo Fisher holder, EDS compatible, with 4 needles for the 4-probe heating function. And this fits very nicely into the goniometer of your FEI TEM. So the whole concept is modular, which makes the tubing and the tip exchangeable, so you can clean them individually. It ensures for a clean environment without cross-contamination between one experiment and the other. And then, of course, it provides results you can trust. Last but not least, it's also a very stable concept. It can easily achieve sub-angstrom resolutions on high-end TEM, and some of our users even managed to achieve resolution figures with this holder in situ conditions, so with gas and elevated temperatures of 55 picometers. So if you want to do heterogeneous catalyst research in your TEM, what will be your typical experimental needs, and how does the climate system meet them? First of all, as we saw, since you're working at ultra high resolution, as you need to see nanoparticles, it needs to be very stable. You want to have low drift when you have these stimuli of gas and heating. And this very stable environment is created by the MEMS sample carrier. Also, of course, you want to know exactly what temperature your reaction is taking place, and also you want to do calorimetry measurements to see the energy which is either produced or required by the chemical process. This we achieve via our 4-point probing system. And also you want to know what gases are produced in the chemical reaction in a nanoreactor. For that, we created a defined gas flow path, so it will be the sensitivity of the gas analyzer can go to very small traces of reaction products. Let's take a closer look at the nanoreactor. So here you see the heating chip for the gel nanoreactor with a pipette, which is drop casting a sample on top of the heater. Then you apply the top chip with an O-ring to seal the volume of the nanoreactor. And in the center of the top chip, you see the membrane where the electron transparent window is located. So the center of the heating chip has, of course, the heating spiral in the center of the membrane. On the heating spiral, you deposit your sample of nanoparticles. Then you start a gas flow, and here you can see what we mean with a defined gas flow path. So the gas is not flowing all over the place, it's flowing exactly within the two parallel lines of the gas flow path. So all of the gas will cross the area where the heated sample is. So there is a maximum chance of gases interacting with the heated sample. Sample is heated by a current via these two probe lines, and then we use the other two probe lines to measure the resistance of the heater, and via the resistance and the calibration process we know exactly what the temperature of the heated sample is. Here you see the same nanoreactor but now in a cross section. So there is an electron beam penetrating from above through the electron transparent window, through the gas layer of the nanoreactor. Then it will interact with the heated sample, which is also on a electron transparent window, and then the information goes into the TEM camera. So the total thickness of the gas layer is for low pressures 5 micron. It can go up to 1000 millibar pressure inside an nanoreactor, which will make the membranes bulge to a total thickness of about 30-35 micron. Then there's a gas in measurement of the pressure and the flow, a gas out measurement of the pressure, and since we measure both the heating current and the resistance of the heater, we can also calculate the power which is needed to bring the sample at a constant temperature. And with this power measurements and the variations in the power measurement, we can also see what energy is required to keep the chemical reaction going. Here we have the gas supply system. So it was designed for the fast switching of the gas. If you see something happening in your TEM image with your chemical reaction and you want to influence that reaction by changing the gas condition, this is the gas system that you will need, because it's not using any mixing vessels. It's using real-time mixing with a low volume mixing valve. So any changes in gas ratio will in a couple of seconds also show up in the nanoreactor. Then we'll in her part of the presentation give you some more examples of that. And the gas mixture is controlled by 3 mass flow controllers. Each gas in that line has a mass flow controller for accurate control of the gas ratios. Then, of course, we have the flexible swing arm to bring the flow controller unit with the pressure controllers very close to the holder with the nanoreactor. Then we have the gas analyzer for measuring the content of the gas flow coming out of the nanoreactor. So here you see an example of methane oxidation with palladium nanoparticles. What you will see happening here is the gas concentration for oxygen going down from 10 to 2%. And then at the start of this animation, first you will see a lot of dynamics in the palladium nanoparticles in the image. But then if time progresses, oxygen content will go down. Also the palladium nanoparticles will slow down. And at the same time, the reaction product of carbon dioxide is also going down. And so you can very nicely see the correlation between gas and dynamics in the TEM image, which is exactly what in situ gas and heating TEM is all about. So this gas analyzer has a specification with a very wide range of the partial pressure sensitivity, because it's using 2 different detectors, the electron multiplier and the Faraday cage. So partial pressures between 10⁻14 and 10⁻4 millibar can be detected here. As I said, all the in situ experiments are controlled by climate software. We will have a separate webinar on that later, so I'll not go in that much detail, but it does provide the user with easy and direct stimuli control. you can do safe experiments, and you can do fast data analysis. It gives you full control of the in situ stimuli, like gas and heating in this case. You also have a very good monitoring system for system integrity. And you can define your own experiment profile. So the experiment will run with even overnight if you're not attending it. Final slide of my presentation shows you the specs for the 3 different models of climate system that we have. I talk most of all about the top end system, which is Climate G+. Can provide you with a temperature up to 1000 degrees centigrade, pressure up to 1000 millibar, and a gas flow rate of up to 1 milliliter per minute. As we say, it's very stable with a low image drift, and it can do real-time mixing of 3 gases. Next to that, we also have a Climate G volumetric blending, which is a new system, has not been shown before. Can also do all the same things as the Climate G+. The only difference is that it will not do dynamic gas mixing, but it will pre-mix the gases in a mixing vessel. So you first need to prepare your gas mix, and only then you can start flowing the gas to the nanoreactor. And finally, there's Climate Air, which is a climate in situ TEM holder without a gas supply system. So the user can hook up his own gas system or just let in air to do an oxidation experiment. Thank you very much. This was my part of the presentation. I do expect Olaf now to hand over to Dan.
Hello everyone, welcome to this webinar. Today I will give you an overview of the applications of our TEM gas and heating system, and also a bit practical technical details in application. As we know, nowadays catalysts play more and more important role in real life, as they can tune the reaction energy barriers to increase the efficiencies in energy conversion, toxic gas processing, etc. The catalytic performance is reported to depend on factors like the particle size, coordination number, and elemental distribution, and so on, or the interplay between these factors. To help find more efficient catalysts, people come to TEM asking for information like size, shape, atomic structure, crystal structure, composition, and chemical bonding, which can be achieved by imaging, diffraction, EDS, and EOS in TEM. The advantages of TEM over other structure analysis techniques are mainly its superior higher spatial resolution and a high energy resolution at also atomic resolution. This has also been revealed in the development history of electron microscopy. We need to see in this process, higher and higher vacuum is pursued to achieve high spatial and energy resolution. However, does this characterization of a heterogeneous catalyst in high vacuum can really reveal what happened in the process? Let's look at 2 examples. As we can see, both of them have the same morphology and structure at the beginning and at the end. While in the reaction process, differences show up. It tells the real active status will not be able to be revealed by pre- and post-mol analysis in high vacuum. Now let's move to a real example and start from a normal TEM image of nickel nanoparticles. From this image, one can see particle size and shape, but hardly conclude anything. Once we mix the hydrogen, oxygen, and helium gas inside, heat the mixture to 730 Celsius degree, one starts to see particles become alive. Some nickel particles are active, catalyzing hydrogen to react with the oxygen, while others not. By comparing these active particles to non-active ones, it is easy to find out that active particles have always clean surface, while sleeping ones have a film covering their surface. More interestingly, we found a very active particle, which is in this yellow circle. It reconstructs its shape every 3 minutes, changing from spherical shape to facet, changing back to sphere after a certain time period. This tells us the thing is believing value in situ TEM helps to straightforward to find different performance and fast to find a real active material and effective to investigate structure-property relationship. As some of you, environmental TEM can also bring up to about 20 millibar gas environment into TEM. Is this already enough? And why do you still need a closed cell in situ gas and heating TEM system? Here is an example of palladium copper nanoparticles shape change differently under different gas pressure. As we can see here, at 600 K under 16 millibar of hydrogen environment, the palladium copper nanoparticles doesn't change anything after about 20 minutes. But if we bring it to 1 bar of hydrogen at 600 K, you can see the particle changes from round shape to gradually to a little bit irregular angular and facet shape from around 3 minutes. So because the surface energy differentiates under different gas pressures, and the real reaction also differs under different pressures. That's why we need to close the cell gas and heating TEM to bring the studies to higher pressure range and also more close to real reaction environments. As introduced by Ronald, now through our climate system, we bring real reaction environment and process into TEM. So what we investigate become dynamic and temporal space come into the game. And we move from ex situ to in situ TEM research by correlating process and structure characterization inside the TEM. Recently, we also bring the real-time gas composition before and after reaction by mass spectroscopy and energy gain analysis involved in endo or exothermic reactions in the process by our built-in calorimetry in the nanoreactor. That is to say, the catalyst performance to be correlated with process and structure. We realized the move from the in situ to Operando. Besides, our software and modular hardware design makes experimental optimization can be done on Benchtop. I will firstly start with in situ applications and come to the other points later on. Here is a recent work from ETH Zurich about carbon nanotube growth on iron oxide nanoparticles. I will give iron oxide a quotation mark here, because actually iron oxide is only the starting composition on the chip, while researchers from ETH Zurich found from atomic resolution images under active environment that the active particle is actually iron carbide. And on the basis of the real-time imaging, they can see that the working catalyst is actually constantly reshaping on the side of the carbon nanotube growth, while on the other side, like on the opposite side of the carbon nanotube growth, you can see it stays nearly static and very faceted, and the morphology doesn't change during this process. This oscillating growth behavior of carbon nanotube growth and the structural dynamics of the carbon nanotube growth inside also strongly indicate that the carbon concentration on this side, on the growing side, is highly also fluctuating during the course of carbon nanotube growth. And actually in this growing process, we also see some is kind of active, some is deactivated. So why some deactivated? So the researchers from ETH Zurich, through this atomic resolution, they find 3 scenarios of deactivation. Here are 2 scenarios. One is 2 small iron carbide nanoparticles they are grown together to form larger ones and deactivate the growth. The other one is actually from the mass thickness contrast here, you can see the iron carbide nanoparticles detach from the carbon nanotube and then stop the growth. And actually now, because of the introduction of gas environment and also the window cell thickness, a lot of people is questioning about the ultimate resolution, like spatial and energy resolution inside the in situ gas and TEM experiments. Let's look at the real image data from Zhejiang University. We can see here in the HRE high resolution TEM at 300 kV, in one bar of helium and carbon monoxide gas environment and elevated temperature of 500 Celsius degree, you can see the ultimate resolution to be about 55 picometer. And the high resolution hard disk STEM images resolution can go to 84 picometer at 300 kV. We can see here actually the image quality is as good as in usual high vacuum and at room temperature condition. We see the performance under static environment. What's the dynamic environment performance? Let's look at this example from EMET. Actually, the researchers from EMET, they use the climate system and changing the gas environment from hydrogen to oxygen. You can see the fast morphology change when they change it from hydrogen environment to oxygen environment. So this is a static view from the dynamic experiment. You can see it started from a little bit facet, a little bit round shape, and go to the hydrogen environment. It becomes very, very faceted, and then go to a very round shape under oxygen environment. And if you return back to the hydrogen oxygen, this is a repeatable process. So actually, we need to know something here is this tomography work uses atom counting from single direction hard disk technique. This technique relies on precise atomic scale comparison between experimental and simulation. It has an extremely high requirement on sample stability in the varying gas environment. Any instability from TEM, sample, or gas control will contribute to the comparison errors. Therefore, from this application example, you can see how the climate system and TEM together delivers even very, very difficult task in an ex situ TEM. And from the crystal structure analysis side, here is an example from Zhejiang University and with collaborations from internal of DENSsolutions. So actually, this is a work to study the nickel oxide to nickel reduction process. What's the different reduction mechanism in the process? So actually, from this graph, you can see as we introduce the hydrogen into the environment, you will see an AEN model, which is a little bit slow reduction process in the first 1 second process. And then it goes to a linear, a bit faster process. And you can also see the morphology change from a little bit round to a little bit hollow structure. And if you reverse the process with oxygen, you can see the morphology is back and the shape is also a little bit reversible. So how we achieve those data? Because we can see here, everything happens just in 1 second. And here is also just something happened in less than 1 second. Actually, we achieved this information through millisecond temporal resolution diffraction technique inside the TEM. So before you watch the video, a hint to how to recognize the differences is the yellow triangle marked diffraction rings, which differentiate the nickel oxide and nickel. So through this example, you can see how because this kind of like millisecond temporal resolution has very, very high requirement also on the sample stability, especially the sample position and height stability of the nanoreactor. So you can see this is from this high stable system, you can achieve a temporal resolution also comparable to in situ synchrotron diffraction. And as we know, actually inside the TEM, if some people use the conventional furnace holder, you know, as the temperature increases, there are also a lot of thermal radiation from the holder, from the grid, from the TEM, which is also a kind of electromagnetic X-rays, similar to the EDS signal. So at the high temperatures, like in the furnace holders, when it reaches about the maximum around 400 Celsius degree, the thermal radiation from the holder and the grid will quickly cover the signal from your sample. That makes the EDS signal cannot reveal anything from your sample anymore. But with our metal heater design, we minimize the heating area and minimize the thermal radiation. Then actually we maximize the X-ray signal from your samples, even at very high temperature. Here is an example from National University of Singapore. They studied the palladium-nickel differences under catalyzing carbon monoxide oxidation experiment. Here you can see before oxidation, before carbon monoxide oxidation and after carbon monoxide oxidation. The catalyst transition from alloyed structure to phase-separated structure. And this EDS is conducted under 650 Celsius degree. This is an example from our users. And practically, you can also go to 700 Celsius degree or even higher temperature. And actually, when it comes to chemical bonding analysis, a lot of people questions about the possibility of yields because of extra thickness involved in this process. We know actually yields is kind of sensitive to thickness. So here is the example from a copper oxide reduction experiment. On the right side, you can see atomic resolution copper oxide nanoparticles on the one bar of nitrogen and hydrogen environment at 300 Celsius degree. On the left side, you can see as we increase the temperature from 50 Celsius degree to 300 Celsius degree, the copper's KH near structure changed from copper oxide, copper 2+ to copper metallic copper status. So through these applications, I wish I can show you if you have, you can do everything at the, when you are doing the characterization at the In Situ TEM, at the ultimate spatial resolution, temporal resolution, and energy resolution as the In Situ TEM. And now in the next session, I will go to the real-time product analysis and real-time energy gap analysis with the combination of what you can do with the In Situ TEM, bring the size, shape, atomic structure, crystal structure, composition, and chemical bonding dynamics together. Before that, I will firstly give an introduction to mass spectroscopy. Here in this graph, actually you can see how we can position the gas supply system, the holder, and the mass spectrometer. And also our software of Impulse, how you can put all of them. And we can see in here, the gas can go from the gas supply system to the holder inside the TEM. And then after going to the TEM, it comes out and go into the mass spectrometer. And after the mass spectrometer, it will return to the gas supply system. So in the next slide, in the next 1 minute, keep attention here, the gas pass from the holder and then to the mass spectrometer. Mass spectrometer back to the gas supply system. It's like here, this red curve is this green line is here the gas coming out of the holder and come to the mass spectrometer. And here the gray line corresponds to here. So actually the gas coming out of the holder, it will come to these lines and part of them will go to the mass spectrometer. And it will first be ionized from neutral gas to the charged particles and go to a mass filter, which is filtered by the mass to charge ratio and go to the detector. Finally, on the screen, what you will see is with the x-axis of mass to charge ratio and the y-axis is the intensity. So here I kind of trying to talk about, okay, you still have some gases need to return to the gas supply system. Why? So let's look at what's the normal mass spectrometer setup. Normally, actually, when the gases leave the holder and come to the mass spectrometer, most of the gas need to enter the mass spectrometer because there is a pump before the detection parts. And this pump will pump nearly most of the gas away. Only a very small portion of the gas can go to the detection part. In this setup, large gas flow is required and slow response time is there. And nanoreactor pressure and flow speed control is limited. Why is this? So look at how we control the pressure and flow rate inside the nanoreactor, because both of them relies on the pressure inside and pressure outside. And here we actually control the pressure to the holder and the pressure out of the holder through the gas supply system. In this setup, actually, if only a small amount of gas can go back to the gas supply system, then actually you lose the control of the outlet pressure. It goes to only like a vacuum as in the pump position. Practically, we need to see we still need a lot of gas to go to the gas supply system. And let's also remember the TEM sample space is very small. So even based on our strategy, we try to minimize the heating area, try to minimize the size inside the nanoreactor. So we will have like about tens of nanoliter of gas can come out of the TEM nanoreactor. And we want gas to control the outlet pressure. We also want enough gas to go to the mass spectrometer. That's why we have a TEM optimized mass spectrometer. We bring the gas detection part very, very close to the valve where you control how much gas into the system, and bring the pump at the back of the detection system. In this case, we minimize the gas to the gas amount to reach the same or even better signal to noise ratio for mass spectroscopy. And by this, we also realize that any gas flow can be detected and faster response time because it's much closer to the valve. And nanoreactor pressure and flow speed is still under control. And what is the calorimetry? We talked about, you see a lot on our website about calorimetry. Calorimetry is a technique to measure heat involved in the physical and chemical process. And when it comes to a gas and heating experiment inside the TEM, water process involve heat transfer. Let's look at the cross section of our nanoreactor. In this process, we have the metal heater to heat up the system. We also have sample and gas need to be heated up. And actually, if the sample react with the gas inlet into the system, there could be exothermic or endothermic chemical reactions, which also can transfer heat from or to the system. And we also need to see there is also gas composition can influence the heat inside this process. Think about in this scenario, think about like you heat up water or a vinegar or some like alcohols. Actually, you also, because of their heat capacity is different, so you need a different heat energy to reach the same temperature. This is analogous to gas composition change. Now let's start first with some Operando TEM example. Here is actually an example from National University of Singapore. Firstly, we can achieve the results from the TEM cameras. From the static images, you can see there's a very faceted and a little bit sawtooth-like structure is inactive in catalyzing carbon monoxide to oxidation experiment. And here at higher temperature, this a little bit rounded shape is more active. And now we bring it to a bit dynamic situation. You see, during this temperature increase from 300 to 500 process, the particle shape changes from very fast to a little bit round shape. And if we reverse the temperature range, you can also see the shape changes from round shape backward to the more faceted structure. So we say, okay, here is the inactive, here is the active. How do you know it? So we have the simultaneously acquired mass spectroscopy data, which you can analyze the gas composition, gas precursor carbon monoxide, and oxygen's composition chain in this process. And we can also see the reaction products, carbon dioxide increase as you increase the temperature. And if you reverse the process, you can also see how it decreases as the temperature decreases. Meanwhile, we also have the temperature and heating power response from the calorimetry inside the nanoreactor. Actually, if you analyze the structure and also the mass spectroscopy data, you can see the transition happens around 450 Celsius degree. And this has also been revealed in the calorimetry data by a spike in the temperature value and also a decrease inside the heating power. Another example is from FHI Berlin this year. So actually from the TEM images, the researchers from from FHI Berlin found that before around 380 Celsius degree, the nanoparticles mainly change the shape from a little bit long and longer like a perimeter to a little bit more round and smaller particles. While after 380 Celsius degree, the morphology doesn't change too much anymore, at least not so observable from the TEM images. While after the 380 Celsius degree, people actually observed mainly the structural change, which relies on the lattice parameter change. And they also revealed this is not something monotonically, like say, okay, I increase the temperature, the lattice expands. It's not like this. Actually, the lattice parameter, it increase, decrease, increase, which is a non-linear behavior there. Now, how to correlate this with what we observed, we say the activity of the those catalysts? Actually, through the mass spectroscopy analysis, people realized from the around like 260 Celsius degree, carbon dioxide start to increase. And at around 380 Celsius degree, there's a very, very sharp increase in the reaction products. And this is also called a ignition reaction inside in the process. So if we look at the calorimetry data, actually in the around 380 Celsius degree, people find a very, very sharp increase on the temperature and also a very, very sharp decrease on the heating power. These are all revealed. So actually, both of the example from FHI Berlin and also from National University of Singapore, it's telling the carbon dioxide reaction is actually an exothermal reaction. When the amount increases suddenly, it releases a lot of energy to the system. It will cause an instant localized temperature increase in our system. But as introduced in the former session, our system have a feedback system, and it want to bring the system temperature back to your control. And then there shows a decrease of the heating power to bring the increased temperature back to the user's control. And actually, because now we can bring the real-time product analysis and real-time energy gain analysis, so which is already showing in the last two slides. So think about that. Actually, you don't really need everything to down on the TEM first. You can firstly use these two functions to find the active, like temperature or active conditions. And then when you say, okay, I can reproduce through our impulse software, then you can go to the TEM and do the size dynamics and shape dynamics and atomic structure dynamics. something you can do for the in situ and bring them together. Actually, now you can bring them together and do Operando analysis. In the next slide, I will show you even more detailed how you do the benchtop experiments. So here is an example of a missing oxidation. A simplified picture is a missing reaction with oxygen and produce carbon dioxide and water. So in this slide, actually here it's a temperature and heating power profiles. And here this is acquired on the TEM. And the bottom two figures are the precursor, gas precursor and gas products from mass spectrometer. So you see carbon, you see methane and oxygen, and here is the carbon dioxide. So actually, what we can see here is, as we go forward and increase the temperature, the carbon dioxide gradually increase, and the precursor methane and oxygen gradually decrease. And to a certain step, the oscillations start to show up. If we zoom to this starting period by doing intersection of using some lines to do intersection of the flat area and the rising up area, you can actually find out the reaction starting temperature to be around 455 Celsius degree. And if you also compare the oscillation starting time, starting with the temperature, you can find it starts to around 725 degree. We briefly mentioned actually this can be controlled and reproduced from the impulse software. This is actually a result just run from a profile. Like I just click start of the profile and leave the computer to control everything and got those results. And if we look at from here, especially for the oscillation, you have up and down, up and down. So maybe you will come to a question, what's the relationship, what's the phase relationship between the reaction and the calorimetry data? So if you see here, the blue curve is the carbon dioxide from the mass spectrometer, and the red curve is the heating power from the calorimetry. As we know, mentioned also in the application examples, carbon dioxide release process is normally an exothermic reaction, which means it releases heat into the environment. And if like here it increase, which means it release more heat in the system. So and then the system temperature will quickly ramp up. And to bring the temperature back to our control, the heating power will decrease. This is what we expect from the theoretical model. This is also reviewed in our experimental result. But is this something what you achieved from the acquisition? From here, you can actually see, well, this kind of antiphase relationship from the final result, like I already did all the data processing and delivered to you. Is the initial status also like this? No. Actually, you can see here, the phase is a little bit messed. What happened there? Let's look at the gas path again. So the gas will travel from the gas supply system to a holder to the mass spectrometer and back to this gas supply system. This is like a person, you're traveling from position A to position B. It takes time to travel. And practically when the software is recording the composition parameters from gas supply system, the temperature and heating power from the nano-reactor, and also as a TEM researcher, you record the TEM image and spectroscopy also at this position. But the mass spectrometer data acquired at this moment, it happens some time ago because it takes time to travel from here to here. And what does it shows in the data? So look at here. We use a simplified model by changing the gas from one stable position to another stable position. From this figure, you can see on the gas supply system, this red curve is in the gas supply system. We change the oxygen gas from one composition to another. It changes instantly. This is what Ronald mentioned in his slide. This is like a real-time and very, very fast gas switching process. And actually, this in the gas supply system, it's instant change. At this time, actually, you don't really see any changes in the mass spectrometer. Only after about 28 seconds, you will start to see some changes in the mass spectrometer. And if you correlate this with what happens inside the TEM, you will see actually after about 20 seconds, the TEM part start to have a reaction. If you do this correlation with your imaging and spectral analysis, this is also the time range you will need wait to see differences. And actually, we also compared what happens inside the TEM and with mass spectrometer. There is about 7 to 8 seconds delay there. Well, and of course, because the temperature and heating power is both of them are located inside the nanoreactor at the same position, there's no time delay between these two parameters. Practically, as a system working under TEM, because there are a lot of work you want to achieve from TEM, you want to bring a lot of things synchronized to the time clock inside the TEM. That's why you need a criteria or method to synchronize all the data to your TEM time. And in this case, you can also see the coincidence of temperature and heating power change with the gas composition change. That's why we use the calorimetry, also say temperature and heating power inside the nanoreactor to bring all the time delays calibrated. Here is a final view of after the time delay calibration. Then you can see once the gas composition changes inside the GSS, and the mass spectrometer starting position also bring to the same position. And also you can synchronize it with the temperature and the heating power inside the TEM. Here we need to differentiate two concepts. One is the gas traveling time, which is like 28 seconds and 7.6 seconds here. This is like one person traveling from position A to position B. And another is the gas switching time of about 32 seconds. How to understand this time? Think about you open your door to refresh your air in your room. Actually, the refreshing depends on if there is a wind and how strong is the wind. And then it decides how fast you can refresh your room completely with the new air. And of course, if you only open a very, very tiny window, the speed will be even slower. But if you open completely one side and the other side, and you have a strong wind, the switching speed will be very, very faster. This is also why we do this like a direct flow control of our gas system. So let's look at, as I showed in the former slide, this is something after time delay calibration. If we don't do this time delay calibration, what kind of consequences would be? This is like we move the mass spectroscopy data a little bit to the right side. The consequences is when you do the analysis, you will see actually you overestimate the critical temperatures, like here, the starting reaction temperature and the oscillating starting temperature. And also you will also mess up the phase relationship when you are trying to correlate the reaction products and your calorimetry. And of course, when it comes to TEM, you will have a messed structure correlations to activities. So these are kind of a model and structure and also benchtop experiment. So here is a summary of what we can do with the climate gas and heating system. You can do in situ and do Operando. And also you can optimize your experimental experiments on the benchtop setup before you move to the TEM. So next, I will show you a practical view. Like say in the former slides, I showed a lot of schematic view and conceptual view, while practically how we realize it. Here is a video from the Impulse introduction video. So this is actually a software. You can control and automate your software, your experiments. Firstly, I will set up my benchtop experiments by connecting all the tubings and assemble the holders. And now you will open the impulse software and select the temperature and gas mass spectrometer control. You need to know here, all the parts are also modular design. You can select the one you want and the part you don't want. And here we can control the temperature and the gas composition to tune to the reactive environment. And you can monitor the precursors and the reaction products and also calorimetries. After you find the proper condition, you can build up the profile with the parameters you want and create your profiles. After the creation of the profile, actually you can load the profile on the benchtop and test if it is reproducible or not reproducible. And after that, we bring the system to the TM. And now we don't need to go to the optimization process. We just load the optimized profile from the computer and click run. And now we leave everything from the DENSsolutions Climate system to the computer. And you can only focus on your TM side, because practically we know you also have a lot of imaging diffraction or EOS, EDS you need to work from your TM side. So through this impulse and also modular design, we save the time and increase the efficiencies in your TM session by minimizing the work from our side. By now, I would like to thank you for your attention and thank you for joining our webinar. Now it's a question time.
All right, so in a moment, I'll open up the floor to any questions. But first, as Dan just mentioned, let me thank you all for your time and your attention. So let's start with some of the questions that have been posted already there. The first question that we have there is coming from Leonardo Lari, and he's asking, what are the conditions that you use during the resolution test, in terms of temperature and gas pressure that gave the 65 picometer resolution?
Actually, the condition is 1 bar of carbon monoxide and helium gas at 500 Celsius degree. The TM is aberration corrected FEI Titan, 80 to 300 kV. The resolution test was conducted at 300 kV.
Perfect. We also have another question from Maria Seo. She's asking if we could give some words regarding the maintenance of the system. How do you clean the system?
So actually, from the gas supply system, of course, I would suggest that as a vacuum system, it's better to pump your vacuum as early as possible. What I mean as early as possible is don't wait before your experiment, then start the pump. So this is like your TM high vacuum experiment. You need to always keep your system at a high vacuum, right? So I would suggest to prepare your system in vacuum condition as early as possible. And after this, normally when we are using gas, so we need to also vacuum the pipelines, because initially your gas pipelines is in the air, and now you connect to our system. So there is still some air inside. If you don't pump away this system, this air, it will also confuse your experiments. You can keep these two together and pump them. And for the mass spectrometer, there is some backout system, which also will firstly back out the waters in your system.
Yeah, maybe if I can add to that on the part of the holder, because of this unique modular concept of the holder, it's very easy in preparation of a new experiment to take out the tip, the O-rings and other tubing individual parts, and then clean them, for instance, in a sonicator. You can also clean the holder in a plasma cleaner, even together with the MEMS chip, yeah, that will also prepare you very well for a clean experiment.
Xiyuan Zhang is also asking if we could explain, or we could give a few extra words on how to optimize the catalyst loading on the chip particularly for mass spectrometry, for calorimetry, and for TEM imaging? How do you optimize the loading of the sample? What do you do there?
Actually, we know for catalysis reactions, there are a lot of sample preparation tricks there, because people want the amount, but people also don't want the particles to be too close to each other. Because sometimes if they are too close to each other, the sintering, like the growth of the particle, could happen during the heating, which already directly deactivate the catalyst. So it's like well, I want as much as possible, but on the other side, I don't want them to be dispersed as much as enough as possible. So from my experiences, you need to prepare your like a starting solvent as dilute, not as dilute as possible, but from my experience, like after the ultrasonic, I will let it stand still for a moment, and then only use the solvent on the top part, which means the particles are quite dispersed there. And then you disperse this like very dispersed solvent on your chip, and try to drop as much as possible. From our experiences, like the clean chips have a color reflection under the light microscope. But if you drop the solvent onto your chip, and with enough samples there, you will see the color, like a reflection, changes to black. And meanwhile, I don't want the large segregations there. In this case, actually, from my experience, you can get enough mass spectroscopy signal, and meanwhile, you guarantee as little as possible sintering happens in the process. So yes, this is truly a bit tricky. But if you want, actually, we can share some pictures to see how to judge this criteria.
We're also getting another question regarding the calibration of the nanoreactors. How does the nanoreactor is calibrated? And they want to know if the time difference between the different components, such as the GSS or the MS, if this is depending on the instrument's geometry.
Well, actually, on the gas traveling time, how to say? Well, it's partially depend on the setup, like how long is your connecting tube, and what's the gas type there. But practically, this is of course also depend on your nanoreactor design, right? So like I said, our direct flow design is kind of like I completely open the door to let the air to be refreshed. But if we have something like our old like liquid system design, we let the gas to immerse, like to disperse from the surrounding channels and gradually to the sample area. This is think about like you changing your air in your room. You just open a tiny window on your window in your room, and then actually this refreshing period will be very slow. So I would say this is a kind of a physical limitation which can be shortened by the nanoreactor design, and can be shortened by the connection tube length.
Hugo, the
Yes?
question on the calibration of the chips, I think you better take that one.
Yeah, so for the chips, indeed, what we do is we rely on different techniques, or we have assessed different techniques to look into the calibration of the nanoreactor, and therefore make sure that the claims that we have on temperature accuracy, they're all valid. So what I can tell you is that we have assessed and we rely on, let's say, a bit more standard techniques, such as pyrometry and Raman spectroscopy. But in this process of assessing and calibrating our microheaters, we have looked into different techniques as well to complement that, such as parallel beam electron diffraction, where for those of you who are not particularly familiarized with this technique, what we do is we sputter the chip with gold. We de-wet it, and then we create gold nano islands, where basically by doing that, you can use each of these gold nano islands as an individual thermometer. And basically by looking at the diffraction patterns, as you heat up, the nano islands, of course, they will start expanding. So then you can start correlating the changes in the diffraction to the temperature. And we've done this, for example, with varying gas conditions to also account for the different thermal capacities that you will have with different gases. But overall, there's different other techniques that we have also used in the calibration of the microheaters, such as, for example, photoluminescence, so nanothermometry based on nanocrystals that through photoluminescence can be correlated as well, or for example using EELs, where we can also monitor the plasmon peaks and how they shift as a function of temperature. So as you can imagine, we have done really an extensive calibration using all sort of different techniques that gives us the confidence that the claims that we have in temperature accuracy are indeed valid. So I hope that gives you a bit more of an idea of how we do that. And of course, one big advantage regarding the chips that we use is the fact that because we're relying on metal, not on ceramics, and because I see that the question is also asking, how do you calibrate each individual nanoreactor? We don't need to work under individual calibration values, but instead, because we're working with metal that has a linear response, that it can withstand a very high current density, then it allows us to make sure that the calibration that we do is on a wafer level, so that when you receive the pack of chips, instead of giving you individual calibration values, you will get one single calibration value for the entire pack that you receive, which will, for example, prevent confusions where if you use the wrong calibration value for the wrong chip, that might lead to problems with temperature accuracy. So that is, of course, something that we prevent. All right, stepping to the next question, very brief question that I see here. If the holder is specific to only Joule TEMs, no, that's not the case. We're also compatible for Thermo Fisher microscopes. And then we have another question that says, have you looked at the influence of the electron beam on the metal oxidation state and reaction? And how do you find any difference when you are doing reaction with and without TEM?
Well, actually, this is a common question, I think not only for In Situ TEM, but also on Ex Situ TEM. So actually, a lot of our research briefly mentioned it also in their papers too. So one way you can try is you can increase and decrease your electron beam dose or dose rate to different level and see if this will change your reactions. If it changes, of course, you need to control electron beam dose or dose rate to a level doesn't modify your reaction. Of course, there are also questions coming about like, initially my reaction is inside a microreactor. Could it be like the confined space in your nanoreactor trigger the reaction? Well, in this case, you can just do do a comparison with an empty nanocell with the gas flow through, and then you bring and compare with if you have the catalyst inside, if there is any differences. So I think those are general questions to TEM society or general questions to a confined space research. You can get the answers from some comparisons.
Okay, and with that we come to the end of this Nanotalk. Thank you all for watching, and I invite you to follow us on our social media accounts, LinkedIn and Twitter foremostly, and also subscribe to our newsletter so you will always be informed if we will organize new webinars. And well, this was it. Thank you for watching and see you soon.